file isn't compatible. All right. So I think we're recording. It's hard to say. Ooh, yeah, view float on top. All right, excellent. So inductors, you know, we hardly learned about capacitors, and we're already learning about inductors. What are we going to do? So a pure inductor is defined as an element in which flux linkage, which you probably never heard of, but is just the integral of the voltage. Not a common quantity to encounter, but it's just defined as being the integral of the voltage. So a pure inductor is defined as an element in which the flux linkage, lambda, across the inductor is a monotonic function f of the current I. In other words, the pure constitutive equation is that lambda is equal to some monotonic function of the current. Now, what does monotonic mean?
One input, one out.
Well, you definitely are on the right track with the one thing. If I speak in monotone, it means it's unvarying, right? It's constant.
Fluctuation.
Yes, and actually, so monotonic function is one that has only increases or decreases, but doesn't do both. So a monotonically increasing function could look like this. A monotonically decreasing function could look like this. You have different rates of decrease, but always decreases or always increases. So that's what monotonic means in that context. An ideal inductor, which is what we will use for our definition most of the time, is such that the monotonic function is linear, with slope called the inductance L. In other words, the constitutive equation is just that lambda is equal to not just any function of I that's monotonic, but specifically a linear function of I with slope L. The units of inductance are the SI derived unit Henry, which is, the symbol is capital H. Most inductors have inductance best represented in millihenries or microhenries. So pretty relatively small compared to the Henry are most inductors. Okay, the elemental equation for an inductor is found by taking the time derivative of the constitutive equation. So once again, we're going to rearrange. So di dt, we're going to put on the left-hand side. Okay, that's pretty good. And we know that that L is a constant, and we can divide it over. Time derivative doesn't affect it. We take the time derivative of the lambda, which up here I defined the flux linkage as being the integral of the voltage. What are we going to be left with? Voltage. So there's our elemental equation, which our elemental equations for each element just relate the current and the voltage. So for the resistor, V equals IR. For the capacitor, dV dt is equal to 1 over C times I. And now for an inductor, di dt is equal to 1 over L times V. So they always relate the current and the voltage. Inductors store energy in a magnetic field. Remember, capacitors stored energy in an electric field. It is important to notice how inductors are, in a sense, the opposite of capacitors. A capacitor's current is proportional to the time rate of change of its voltage. An inductor's voltage is proportional to the time rate of change of its current. So they're sort of dual in that sense. Inductors are usually made of wire coiled into a number of turns. The geometry of the coil determines its inductance, L. So the geometry includes things like the diameter of the wire used, the diameter of the coiling, the wrap, and number of turns of the coil, and the whether or not there's a core in the coil. So you can wrap it around a core or have what's called an air core, which is no core material. So often a core material, such as iron and ferrite, is included by wrapping the wire around the core. This increases the inductance, which is why we do it. Yeah. You will see just air core inductors, though. If you're in the lab, there are some, and it's really easy to spot them because they just look like it's a little coil. And you can even see it. A lot of them are encased in some plastic. Okay. Inductors are used extensively in radio frequency or RF circuits, which we won't discuss in this text, so in this class either. However, they play important roles in AC to DC conversion, filtering, and transformers, all of which we will consider extensively. So, some stuff to look forward to. The circuit diagram for an inductor is shown in 1.5. So it just looks like a coil, which makes sense. And like I said, it's constructed with a wire that's wrapped around something. So remember, for a capacitor, it can act as an open circuit. Well, an inductor can act as a short in certain situations. So if, for instance, there is no current change, the voltage across it is 0, right? There's no current changing, then V's got to be 0, because this side's 0. So there's no voltage difference across this inductor, which means that it's acting as a wire, right? There's no voltage across it, it's just a wire. So in steady state, or what some people would call like a DC situation, an inductor acts just as a wire. But there's some interesting aspects. So inductors, so you may have heard things like, it's hard to drive an inductive load, or it's hard to power an inductive load. Or you got to be careful when you're powering an inductive load. And in particular, the inductive load we care about most is the motor. The motor has coils in it that create an inductance in the motor. And we'll talk more about motors later, but for now, we know that there are some coils in motors that make them work the way they do. And so these coils create inductance in the motor. So there's going to be some inductance in the load that we're driving when we drive a motor. Now, what happens if you're driving a motor along and you're like, I'm done with this. I want to shut the motor off. So you flip the switch. Your current flowing through the inductor, maybe it was at a steady state. Maybe it was constant current flowing through. Let's say that you were driving like a pretty beefy amount of current through. It doesn't really matter though, any amount. So just say 1 amp, just going into your motor. Just constant, you're in steady state operation, current wasn't changing. And then you flip the switch, so there was no voltage across it, wasn't really doing much. And then you flip the switch, which doesn't allow current to flow, right? It drops down to 0 amps. Flip that switch. Now, what is the voltage when you transition? What's the voltage across the motor? So remember, the voltage is going to be proportional to the time derivative of the current. Yeah, it's like infinite. right here, right? The derivative of this thing, it changes, in fact, not instantaneously, but essentially instantaneously, very, very quickly. It goes from some finite current to no current, and so the derivative of that is huge. I mean, hugely negative, but in either case. So you're looking at a huge voltage across your motor that whatever the driving circuitry is going to see, right? It's going to see, it's got a motor in the circuit, and you flip the switch, and there's this huge voltage that gets built up, like instantaneously, just bam. And this is called inductive kickback, or sometimes blowback, and it can really damage things. So, especially the driving circuitry can really damage. It can also break down if there's a certain, if you get to a certain voltage across a gap, it'll arc. You can get that to happen as well if you get these huge voltages. So you can, if you have arcing, that can wear things out really quickly. It's just overall, it's a bad thing to do. You don't want to have these massive voltage spikes, especially if you have any digital electronics that are connected to it. Those will get fried. So we have to deal with this sort of thing when we have inductive loads that we drive. And there are ways to deal with it, and I'll talk about some of those ways. You can use like a component that we haven't learned about yet, which is a diode, but we'll learn about it next week. And a diode flows current only in one direction, so we can sort of put a little shunt in and get rid of this this difficult problem. But it's just the type of thing that we have to be aware of, and this is why we can start to get an intuition about, okay, inductors, they are really sensitive to a fast change in current flow across it. You got to be careful if you flip a switch when you have an inductive load. What are you going to do with the spike in voltage that's going to be created? So, okay. Any questions on inductors? Is it Friday? Okay, good. Yes, I'm excited for this weekend too. Are the Seahawks gonna win this weekend?
Yes. Probably.
God, I really want them to win. So I told the last class, I grew up, my dad was a Miami Dolphins fan, and so I grew up with, liking a team that lost all the time. And when I moved over here, I was like, oh, okay, like Seahawks, I should be a Seahawks fan. It's a local team. And it was easy because they're like starting to get good. This was before they were actually good, but they were starting to get better, and I was like, oh yeah, cool, and Russell Wilson, surprise, is actually pretty good. Okay, cool. But now it's like it's awesome, peaking, and I'm like, oh my god, this is so great, liking a good football team that wins games, and I got used to it.
That did feel good.
And I just don't want to go back to liking a team that loses all the time. So I really hope that, last season was kind of a fluke. Our offensive line picks it up like 5 notches or so.
I was going to say a lot of
Yeah. So in any case, I am very concerned about the Seahawks this weekend. I mean, they should win, which is always a problem. So. All right, guys. Well, have a good weekend. Some of you I'll see in class this afternoon.